First video podcast for HYD 51 covering the material that's going to be in the course and giving you an introduction to that material. So the earlier video podcast just dealt with the structure and understanding what active learning and learning-centered education was about. Now I want to give you an introduction to the specifics of HYD 151. And first I'm going to show you what topics are covered in the course. This is also available in the syllabus information on the course website. If you go to pasternak.ucdavis.edu, click on Teaching, and then click on HYD 151. So this course is divided up into several logical units. I hope it will make sense. The first part is that in practice as a professional hydrologist, there's a lot that you can and should do before you even consider going out in the field. Of course, it's very expensive to do field work, so you only want to go out in the field when you've exhausted the available resources to understand the hydrology of the situation based on, desk available information. And more today is available. But the other part of it is you really want to set up your experimental design prior to going out in the field. Now, I don't want to say that going out in the field is unnecessary, far from it. There's nothing more valuable than doing a recon and getting out into the setting where you're doing the work and getting some experience with it. Never formulate an opinion about a site until you've been there, unless there's some really extenuating reason why you can't do that. So the first part of this course is a suite of topics associated with what you should do before you try to go out and measure things. I've already in this lecture I'll just hit a few points about basic hydrology. Then the first substantive video podcast will be about geographical positioning methods. Then I'll cover historical analysis. Then I'll cover types of field hydrology studies. Then we'll look at experimental design and spatial characterization. And then finally automated data acquisition. Now, ideally, I'd like to cover all of these topics before we start on any of our field trips and field work, but the reality is that it sort of works out best to intermix some things. So even though this is part one, we will do some of part two intermixed along with part one. But just conceptually, these things come first. In part two, we'll look at precipitation and runoff, and for all of the different things there, we'll worry about direct measurement of flux and storage, but also about collecting samples. Or there may be things where we want to characterize something in situ, like surface sediment sampling. We'll also look into some allied topics related to hydrology, things like sediment, water quality, and even stream channel assessment, because when we're looking at rivers or possibly lakes or other bodies of water, then it's helpful to have an understanding of the nature of that entity, not just the water that's flowing through it. Okay, then we'll look specifically at water quality, and we'll look at that in different settings because how you sample is different depending on where you do that. We'll also look in the subsurface at hydrogeology, specifically related to the things we do in field measurements like well construction and sampling from a coring device of some kind. And then we'll look at the plot scale water balance, so the soil physics kind of stuff that you may be getting in the soil physics class, but plot scale water balances, how to deal with a forest water balance, infiltration, evapotranspiration, things like that. And then finally we'll look at some advanced topics, the use of hydrology in things like environmental restoration, or how to innovate to measure things that haven't been measured before. And we'll also look a little bit at an example of wetland hydrology, since I have some expertise there. Besides these specific topics of the video podcast, of course the class itself involves a lot of field trips. And so in the field trips we'll be going into depth about the trade-offs of different sensors that you would use in different settings. And we'll also have a project for the course in which you'll be able to do something far more substantive, integrating across different topics. Okay, well I just have a few slides to just get you back into the swing of things with hydrology. Hopefully you've had some kind of introduction to hydrology class or something else. But if not, some of these basic topics will give you a good starting point. And surprisingly, I've noticed that even by the end of a class like this, if I come back to the fundamentals of what hydrology is all about, students may have forgotten, like they just get so caught up into the details of field methods that they lose sight of the big picture. So it's important to reflect on what hydrology is at its heart, and so think about that as we look at these next few slides. Of course, the hydrologic cycle is really the core of what this is all about. The idea that water is stored in different places around Earth, so spatially distributed, and then that abundance varies through time. And water fluxes, it flows, it moves, it transfers, whatever term you want to use, but it gets from one place to another, one storage area to another, and so we have to be able to characterize that flux. And then finally, it interacts with a bunch of allied things like sediment and other chemical constituents, physical properties like temperature, density might come into play. So overall, the movement, storage, and interaction of water and other things is what hydrology is all about. The number one tool that you need to know and be able to use as a professional hydrologist is the hydrologic budget. So let's play a game. If I were to say to you, I want to hire you to assess contamination that might be coming out of the septic tank that's under my gas station, what tool would you use to do that? Well, the first thing you should say is, I'm going to do a hydrologic budget. Or if I ask you, I want to know if contamination up in a watershed, where is that going and what are its consequences? I want to do a hydrologic budget. If I want to know what's the future of the snowpack in the state of California, I'm going to do a hydrologic budget. So when I come back to you at the end of this class and give you some more sophisticated scenarios and ask you, what are you going to do? Hopefully you'll remember that you're going to do a hydrologic budget. Of course, there's much more to hydrology than just a hydrologic budget, but it's always the great starting point. It's the first place you go because it tells you what are the relative scales of water fluxes and water storages in the system. Where should you focus your effort? Where the sensitivity is going to be? So having made this big plea to focus on a hydrologic budget, it might be helpful if I actually tell you what one is. But it's nothing more than a statement of mass conservation. And we have three really big natural laws that we worry about in physics, one of which is conservation of mass. And we can also be interested in conservation of energy and conservation of momentum in terms of conservation laws anyway. But for right now, we want to focus on the conservation of mass, and in terms of mass, it's the mass of the water. So you could also write mass statements for sediment or chemical constituents or heat, but we're not going to do that right now. So for hydrologic budget, you have to say, what's the area of interest that I have? It's going to be a field, it's going to be a watershed, it's going to be a gas station, like whatever that area is going to be, you need to specify that. Then what the budget is going to do is it's going to tell us the relative proportions of stuff moving in or out or changes to storage in that system. And it's going to give you insights to help you figure out what are the key processes that are at work in different systems. Okay, so let's look at two different examples at different spatial scales. The first is going to be a small scale plot. So this could be an agricultural plot, it could be an urban setting or something like that, but usually we think of it as just like a natural terrain landscape or an agricultural area. So imagine this block that's shown here on the slide I'm looking at and you're looking at. It's got a 1 meter by 1 meter plan view dimension. So it's it's like a single square, 1 meter by 1 meter. And then I've given it a dimension and elevation so that it's 1 millimeter thick of soil with 1 millimeter of air above it. So in this case, the water balance expresses the inputs that are balanced by the outputs and the storage that's there. So the inputs would be, say, precipitation coming in from above, and then run-on coming from whatever is upslope, that gravity is pulling water down along the surface and it might run through the plot. If it's completely horizontal and there's no run-on, then so be it. Note that we use the symbol Q to indicate discharge. And run-on is a form of surface discharge, so therefore you'll see Q with the subscript in, and then on the other side, Q with the subscript out. So whatever water is coming in, some of that could be leaving on the surface. We also have E for evaporation because we have bare soil. Water can be evaporating off the surface of the soil if it's ponded. It could even be evaporating from the pores within the soil as well. Here I'm using the letters I and F for infiltration because the letter I is used in a variety of contexts, and I don't want to just use that. Other people use Z or F in other instances, but just trying to keep it simple here. In terms of infiltration, this is water leaving this top millimeter of soil and going down. So it's a very shallow form of infiltration. We're basically just saying that this 1 millimeter of soil and 1 millimeter of air is the contact at the Earth's surface, and anything that goes down below that is infiltrating into the soil. And then I've got SM here, which stands for soil moisture, and it just reflects the fact that some amount of water, usually, could be a moderate amount, is stored in the soil itself, and that could be changing through time, or it could just be a steady amount that's not changing. And that could be a plus or a minus, just depends on what's going on with it. If it's not changing through time, it might even just zero out of this equation. So it just depends how that's done. So these could be units of length. They could be, like millimeters of water. It could be volumes, cubic meters of water. Could be length per time or length, volume per time. So there's a lot of different ways depending on your specific circumstances for how you would play that out. The last thing I want to say, if you really want to get nitpicky, there could be some water vapor in the air, and I haven't included that here, but theoretically it could be there. So overall, just looking at this simple plot, hydrologic budget means to characterize the ins and outs at the scale of interest that you're looking at. So let's move to another scale. So here's a watershed. We haven't really gotten to this. Hopefully you've heard this term before, but the idea of a watershed is just that it's all of the land that drains to a designated outlet. In this case, the outlet is in the lower left, so I'll move the arrow over to that area and sort of circle it. That's the outlet, so this is the kind of a three-dimensional oblique block showing all the water going there. And this control volume or area of interest doesn't include the air, but it includes the ground surface and the subsurface down to this bedrock contact. So imagine you could have a weathered mantle of soil that's like 1 to 2 meters deep. This could be a hill slope, or a relatively small watershed, say 1 to 5 square kilometer area, something like that. So when we do a water balance for this, we have precipitation falling onto the surface. But instead of just having evaporation, E, if the surface has vegetation, and virtually all natural surfaces on Earth do, then we say ET to lump together the bare soil evaporation and the vegetated transpiration that's going on. Or we could see it all as one lumped surface, so to speak, with a mixture of plants and soil that together have an overall effect of ET. There's no groundwater inflow or surface runoff in this case because we're considering this topographic divide to be a barrier for flow. That's why we call it a watershed and have that boundary. However, both surface water, Q here is stream flow, or possibly a little bit of underflow or what we call hyporheic flow, could be leaving off the surface. We could also have groundwater flow where the bedrock could be fractured. And so what's interesting about this statement of the water balance is that you don't see soil moisture as a term. And that's because in this case, well actually I take it back. Okay, so soil moisture is a storage term that might be there. But infiltration, that's what I meant to point out. Infiltration isn't a term because the flux of water from the surface into the soil is not at the boundary of this control volume. Groundwater out is at the boundary. So here, soil moisture is not just that 1 millimeter thin zone, but is the totality of the soil down to this bedrock contact, and therefore the outflux is groundwater out. So it's a different spatial scale. The totality of soil moisture is here. We also have what's called depression storage. That's water that's ponded on the surface, and that could change through time. So depending on whether these storage terms are changing through time or not, if there's no change, then they would simply zero out, and you could have inflow equals outflow, something like that. The last concept I want to introduce you to here is to just tell you that there is a component of hydrology that's experimental in that it actually goes out and tries to do manipulations the way a biologist might do an experiment in a laboratory, or a chemist might do that. We have experimental watersheds. They tend to be smaller in order to do meaningful comparisons. But here's one of these, the COETA Long-Term Ecological Research Site, LTER, and there's a website here if you want to learn more about it. So on the left is a photo of this small watershed from December 1940, showing it as it existed. So they could have monitored this for 10 to 20 years or something. Then they cut it and they apply herbicide to keep the vegetation from coming back. And you can see a year later in July 1941, well, this is only 6 months later, I guess, but this fresh cut terrain. And so understanding, this is field science, but at a full-scale experimental domain. And we will be looking at this in more detail. So that's all the introduction that I wanted to give you. Just remember the water cycle, the water balance, and we're going to be looking at how you apply those both in an experimental context as well as in a variety of other contexts that we'll see.